Somewhere over the Pacific right now, a storm is breaking the rules. Last night the models called it weak. This morning it has doubled its winds and no one saw it coming. You're about to meet the storms that defy every forecast we trust. A hurricane that jumped from gentle to monstrous in a single day. A wall of wind that rebuilt itself while scientists watched, helpless. An ocean so warm it feeds these giants faster than we can measure. A theoretical superstorm so violent it should not be able to exist. We will fly straight into the eye, drop into the ocean's hidden heat, and stand at the edge of what science can predict. If storms that outsmart our best supercomputers pull you in, hit like and subscribe. The rules we thought we knew are about to bend. Prepare yourselves. We begin. It is 2 a.m, and the storm on the screen is fooling everyone. A forecaster sits in a dark room, coffee going cold, watching a small swirl of clouds far out over the ocean. The computer calls it nothing to worry about. A weak storm, maybe some rain for a few fishing boats. The forecast for tomorrow promises a mild system that will drift and fade. The day crew heads home. The night shift takes over. Then the storm begins to change. At first the shift is small. The clouds tighten. The centre pulls together like a knot being cinched tight. On the satellite loop the storm spins faster and faster, and the forecaster leans in. The numbers look wrong. The pressure at the middle of the storm is dropping like a stone falling down a well. When pressure falls that fast, it means the storm is feeding. It grows stronger by the minute, and nothing in the forecast warned that this would happen. By sunrise, the harmless swirl has a clear eye. A dark circle sits at the centre, calm and quiet, wrapped in a wall of screaming wind. In a single night, a storm the models called gentle has become a giant, and a coastline full of sleeping people has no idea what is racing toward them. This is the nightmare that keeps storm scientists awake, and it happens more than you would think. Here is the strange twist. When it comes to guessing where a storm will travel, forecasters have become almost magical. They can tell you, days ahead, which stretch of coast a hurricane will strike, often within a few miles. Picture guessing where a single leaf will land after it floats across an entire football field and nailing the spot. That is how sharp our aim has become on the path. The path, though, is only half the danger. The other half is power, and power is where all that skill falls apart. A storm can hold its course exactly as predicted and still surprise us with a punch no one expected. A system the models swear will stay weak can double its winds overnight. When that happens, the people in its path lose the one thing that keeps them alive: time to run. Scientists have a name for this sudden, violent growth. They call it rapid intensification. It is the hardest trick in all of weather to see coming. A storm can gain 35 miles per hour of wind speed, or far more in a single day, turning from a shrug into a killer while a city sleeps. Over the last few decades, storms have been pulling this move more often, and pulling it faster, and forecasters are scrambling to learn why. To understand how a storm can outsmart a room full of scientists and supercomputers, we have to start with a puzzle. Somehow we cracked the impossible problem of the path. We learned to trace a storm across thousands of miles of open ocean and point to the exact town it would find. So how did we ever get that good? And why, after all that genius, does the storm's raw strength still slip through our fingers like smoke? The answer starts with a shrinking shape on a map, and a discovery that changed everything. The shape on the map is called the cone, and once upon a time it was enormous. When forecasters draw a hurricane's future, they do not draw a single line. They draw a cone, a fat wedge that spreads out from the storm and shows every place it might end up. Decades ago, that cone was so wide it was almost useless. A storm 3 days from land might hit anywhere across hundreds of miles of coast. So officials had to warn everyone. Whole regions boarded up windows and fled when the storm would strike only one town. People stopped trusting the warnings, and that is dangerous, because the day the warning is right, nobody listens. Then, slowly the cone began to shrink. The reason sits high above the storm. A hurricane does not choose its own path. It gets shoved along by giant rivers of wind that flow through the upper sky, currents called steering winds. Think of a rubber duck dropped into a stream. The duck spins and bobs on its own, but the stream decides where it goes. A hurricane is that duck. Those upper winds are the stream. Learn the stream, and you can guess where the duck will drift. The trick was learning the stream, and that took eyes in space. Weather satellites changed everything. Floating far above Earth, they watch the whole sky at once, tracking those steering currents as they swirl and bend across the planet. Down on the ground, supercomputers swallow all that information and run the physics of the air forward in time, hour by hour, calculating where the winds will carry the storm. Every year the satellites got sharper, every year the computers got faster, and every year the cone got a little bit smaller. The change is stunning. Over about 30 years, the average mistake in a storm's predicted path has shrunk by more than half. A 3-day forecast today is roughly as accurate as a 1-day forecast was back then. We doubled how far into the future we can see. Forecasters now point to a stretch of coast, days ahead, and say the storm will land here, and again the storm obeys. That is a quiet miracle. Guessing the path of a churning 1,000-mile monster across open ocean is one of the great wins of modern science. It has saved countless lives, giving people time to leave before the water rises. But nature kept one secret back. Because while the path grew clear, the storm's strength stayed hidden in fog. Forecasters could tell you exactly where a hurricane would arrive, yet have no idea how hard it would hit when it got there. They might promise a mild storm for a town, and watch in horror as a monster came ashore instead. The steering winds that guide the path are big and slow and easy to read. The forces that control raw power are small and fast and buried deep inside the storm where almost nothing can reach them. For years, one clue offered the best early warning that a storm was about to turn dangerous. A single number read straight off the instruments. When it starts to fall, forecasters sit up straight, because a falling number means the beast is waking. That number lives at the dead center of the storm, in the strange calm of the eye. And understanding it means understanding what a hurricane really is. At the middle of every hurricane hides a hole in the air, and its depth is the whole secret. We do not usually feel it, but the air above our heads has weight. Miles and miles of it press down on you right now, on your shoulders, on the top of your head, on the ground. Scientists measure that weight as pressure. On a calm, ordinary day, the pressure at sea level sits at a steady value that almost never moves. It is the quiet background hum of the sky. A hurricane rips a hole in that hum. At the center of a hurricane, warm air rushes upward in a furious column, carrying moisture high into the sky. As all that air lifts away, it leaves less air behind, pressing down. The weight of the sky, right at the storm's core, drops. The deeper that drop, the more powerful the storm. So forecasters watch the pressure at the center the way a doctor watches a heartbeat. It is the single clearest sign of how strong a hurricane truly is. This number matters for a simple reason. Air always rushes from high pressure toward low pressure, the same way air screams out of a popped balloon. The bigger the difference, the harder the rush. A hurricane's low center is like that balloon, pulling air toward it from all around. The deeper the hole, the faster the surrounding air comes howling in, and that howling inward air is the wind that tears roofs off houses. Picture the storm as a drain in a bathtub. A shallow, weak drain barely tugs the water. A deep, powerful drain creates a roaring whirlpool that sucks everything toward it. The pressure at the center measures how deep that drain goes, and when the number starts falling fast, it means the drain is opening wider by the hour. Now the numbers themselves. On a normal day, the sky presses down at a little over 1,000 of the units scientists use to measure it. A strong hurricane can push that number down toward 900. The most violent storm ever measured on Earth drove it all the way down to around 870. That storm's winds reached over 200 miles per hour, fast enough to lift a car off the ground and throw it. This is the number that gives forecasters their first warning. A storm can look ragged and harmless on the satellite, yet if the pressure at its core is dropping like a falling elevator, the scientists know something violent is coming even before the winds catch up. And that is the cruel twist of it. The pressure often falls first. The wind follows after, so there is a terrible window, sometimes only hours long, where the instruments scream danger while the storm still looks tame from the outside. A forecaster can see the beast waking in the numbers and still struggle to convince a sleepy town to run. So scientists needed a hard line, a clear rule that says, once a storm crosses this point, treat it as a monster no matter how it looks. They needed a way to name the exact moment a storm goes from ordinary to extraordinary. They found it, and they wrote it as a single, chilling threshold, a speed a storm must gain in just one day. Cross that line, and forecasters use a word they almost fear to say. The word forecasters fear is not loud or dramatic. It is a plain measurement, and that is what makes it terrifying. Scientists drew a line in the sand. When a storm's winds speed up by at least 35 miles per hour inside a single day, they give it a name: rapid intensification. That may sound gentle, almost polite. It is brutal. 35 miles per hour of extra wind in one day can shove a storm up an entire category, turning a manageable system into one that flattens homes. And 35 is only the doorway. Some storms blow far past it. The wildest storms have gained 100 miles per hour of wind speed, or even more in the same 24 hours. Picture a storm waking up as a strong breeze you could walk through, and by the next morning howling with winds that can peel the walls off a building. That is the difference a single day can hold. The record breakers have gone from a gentle first category storm to the top, most violent category in about a day, a leap that used to take a storm the better part of a week. To feel how fast that is, imagine a car sitting still at a red light. Now imagine it hitting highway speed in the blink of an eye, then doubling that, then doubling again, all before you could finish your breakfast. That is a storm in rapid intensification. It is the atmosphere flooring the gas pedal. So why do forecasters lose sleep over it? Warnings run on time. When a storm strengthens slowly over days, a coastal town gets a long, calm runway to prepare. People board windows, families pack cars. The old and the sick get moved to safety. But when a storm explodes overnight, that runway vanishes. A town that went to bed expecting a rainy day wakes up to a monster already at the door with no time left to run. That stolen time is measured in lives. The most feared storms in history share this one trait. Again and again, the deadliest, costliest hurricanes were the ones that intensified rapidly right before landfall, catching everyone off guard. Slow storms give warnings, fast storms give funerals. That is the brutal math forecasters carry every hurricane season. So the giant question, the one that hangs over every storm center on Earth, is simple to ask and maddening to answer. Which storms will do it? Two storms can look almost identical, sitting over the same warm ocean, under the same blue sky. One fizzles into nothing. The other detonates into a nightmare. For decades, scientists could not reliably tell them apart. A storm would cross that 35-mile-per-hour line while the models insisted it never would. To predict rapid intensification, you first have to understand what feeds it. What is the fuel that lets a storm double its strength while we watch, helpless to stop it? The answer is spread across millions of square miles, and it's something you have felt yourself on a summer day at the beach. The ocean is more than just water. Under the right conditions, it becomes a battery, storing a staggering amount of energy, waiting for a storm to come along and spend it all at once. And the warmer that water grows, the more dangerous these storms become. Every hurricane on Earth is born from warm water, and it needs that warmth to be almost bath temperature. A storm is a heat engine. It runs on the warmth stored in the top layer of the ocean, and it turns that warmth into wind. Here is how. When ocean water is warm enough, it evaporates fast, lifting invisible water vapor up into the air. That rising vapor carries heat with it. High in the sky, the vapor cools and turns back into rain, and as it does, it dumps all that stored heat into the storm. The heat makes the air rise even faster, which pulls up more warm vapor, which releases more heat. Round and round it spins, feeding itself, growing stronger. Cut off the warm water, and the whole engine dies. Scientists found the magic line. The ocean surface needs to reach about 80 degrees Fahrenheit before a hurricane can really get going. That is roughly the temperature of a warm swimming pool, the kind you can float in for hours without a shiver. Below that line, storms sputter and fade. Above it, they wake up hungry. And the warmer the water climbs past that mark, the more fuel the storm can gulp down. Think of the warm ocean as a giant tank of gasoline, spread thin across the surface of the sea. A storm rolling over it is a car with the tank wide open, drinking as fast as it can. Cooler water is an empty tank. The storm coasts, then stalls. But send that same storm across a stretch of extra warm sea, and it stomps the gas. This is why the map of warm water matters so much. Before a big storm, forecasters study charts of ocean temperature the way a general studies a battlefield. They hunt for the hot patches, the places where the sea has warmed past that 80-degree line, because those are the spots where a storm can suddenly find a second wind and explode. And the oceans have been running a fever. For the last few years, the surface of the sea has been hotter than any period ever recorded, and by a wide margin. vast regions of the tropical ocean now sit well above that magic line for months at a time. In parts of the Pacific, the water has climbed past 86 degrees, warm as a hot tub, stretching across an area larger than several states combined. That is a tremendous amount of stored fuel sitting and waiting. More fuel means more of these sudden, violent surges of strength. When a storm crosses one of these overheated patches, it can find exactly the energy it needs to double its winds overnight. The warm surface is the reason rapid intensification is happening more often, and forecasters know it. But the surface is only the beginning of the story. The temperature you feel when you dip your toes in the water tells you almost nothing about what lies beneath. A storm does more than skim the top of the sea, it reaches down. And what it finds below the surface can decide in a matter of hours whether it grows into a giant or falls apart. Because the real fuel, the hidden reserve that powers the most monstrous storms, lies far below the surface, deep where our instruments struggle to see, in warm water no swimmer ever touches. The ocean has a secret that the surface never reveals, and it decides which storms live and which ones die. Warm water at the top of the sea can be one of two very different things. Sometimes the warmth is only skin deep, a thin heated layer floating on cold water below, like a warm blanket laid over ice. Other times the warmth reaches far down, hundreds of feet of heated water stacked on top of itself, a deep vault of stored energy. From a satellite, from a boat, from the beach, these two oceans look exactly the same. The surface temperature reads warm either way. The difference hides underneath, and that hidden difference can make or break a hurricane. Here is the trick. A hurricane is a violent thing. Its winds do more than glide over the sea, they churn it, stirring the water like a giant spoon. That stirring drags up whatever lies below. If cold water sits just beneath the thin warm layer, the storm pulls that cold water to the surface, and, in a strange way, poisons its own fuel. The sea under the storm turns cold. The engine sputters. The storm, in effect, puts out its own fire. Scientists have a name for how much warmth is stored down deep. They call it ocean heat content. It measures the whole reserve top to bottom, the true size of the fuel tank. A high ocean heat content means the warmth runs deep, and no amount of churning can reach cold water. The storm stirs and only finds more warmth waiting. It feeds without limit. Picture two phones, side by side, both showing a full battery on the screen. One dies within minutes because its actual battery is tiny. The other runs all day because its battery is huge. The number on the screen looks the same. The real difference is hidden inside. Surface temperature is that number on the screen. Ocean heat content is the true size of the battery. And the storms that terrify forecasters are running on the biggest batteries in the sea. This is the fuel that models miss. A satellite can read the surface of the sea beautifully, mapping the warm and cool patches from space. But no satellite can see down into the water. Measuring the deep heat means dropping instruments into the ocean itself, and there are never enough of them, scattered across a sea that covers most of the planet. So the deep warmth often stays a mystery until a storm plows right over it and suddenly, shockingly, blows up. Some of the worst forecast misses in history happened for exactly this reason. A storm crossed a pool of deep, hidden heat that the models did not know was there. The fuel tank was far bigger than anyone realized. The storm drank it down and exploded into a giant, while forecasters stared at their screens in disbelief. So warm water, deep and vast, is the fuel. It is the first ingredient every monster storm needs. Yet fuel alone is never enough. You can pour gasoline across the whole ocean, and most of the time no monster forms at all. Something else has to be right in the sky above. Because high overhead, a second force is always at work, and it holds the power to strangle a storm before it ever gets started, no matter how warm the water below. High above every storm, an invisible knife waits, and it can slice a hurricane apart before it ever becomes one. A hurricane is a tall thing. To grow strong, it has to stand up straight, a towering column of spinning clouds reaching from the warm sea all the way to the edge of space. The storm stacks its power vertically, layer on layer, like a spinning tower built of wind. As long as that tower stands tall and straight, it can gather strength, pulling heat up from the ocean and spinning faster and faster. But the winds high in the sky do not always agree with the winds down low. Sometimes the air near the surface blows one way, while the air miles above blows a different way or a different speed. Scientists call this difference wind shear. When shear is strong, it grabs the top of the storm and shoves it sideways while the bottom stays put. The tall tower tilts. It leans, and a leaning storm cannot hold itself together. The warm air rising from the sea gets blown off to the side before it can do its work, and the whole engine falls apart. Picture a spinning top. When it stands upright, it spins smoothly for a long time, steady and strong. Now imagine flicking the top of it with your finger while it spins. It wobbles, tilts, and quickly falls over. Wind shear is that flick. It topples the storm before it can find its balance. This is why a calm, quiet sky high above can be the most dangerous thing of all. When the upper winds go still, when the shear drops to almost nothing, the storm gets to stand perfectly straight. Nothing knocks it sideways. Nothing tears at its top. Every bit of heat it pulls from the ocean goes straight into building more strength. Forecasters watch for these windows of low shear the way sailors once watched for calm seas, because low shear over warm water is the recipe for a monster. It is the moment a storm can truly let loose. The most explosive storms almost always form in these pockets of calm upper air. Low shear, deep warm water, and a storm sitting right on top of both. When those ingredients line up, a system can gain 60, 70, even 100 miles per hour of wind in a single day. The atmosphere pulls back every restraint, and the storm sprints toward its full and terrible potential. Shear is the great referee. High shear keeps storms weak and scattered, ripping them apart as fast as they try to build. Low shear lets them off the leash, and forecasters have gotten fairly good at spotting where the shear will be high and where it will be low, which helps them guess which storms have a chance to explode. Yet even here, the storm keeps a few tricks. Warm water can be deep, the shear can be low, everything can look perfect for explosion, and still the storm falls flat on its face. Because there is another hidden enemy, one that rises from neither the ocean below nor the winds above. This one rides in on the air itself, invisible and dry, and it can choke a storm to death from the inside out. A hurricane needs wet air to breathe, and a mouthful of dry air can strangle it in hours. Everything a storm does depends on moisture. The warm, damp air rising off the ocean is the storm's food, its breath, its whole reason for living. That moist air climbs, cools, turns to rain, and releases the heat that powers the winds. A storm swimming in humid air is a storm that can grow. It has everything it needs, all around it, in every direction. Then a river of dry air arrives, and everything changes. Deserts breathe out enormous plumes of hot, dry air that drift for thousands of miles across the ocean. When one of these dry plumes wraps into a storm, it acts like poison. The dry air sneaks into the core and kills the rising columns of warm, wet air. Instead of climbing and raining and releasing heat, the air just sinks, parched and empty. The storm gasps, its engine coughs and stalls. What looked like a growing hurricane can fall apart in a matter of hours, unravelling into a shapeless smear of clouds. Picture trying to keep a campfire roaring while someone stands beside it, fanning cold, dry air straight into the flames. The fire needs to build heat to survive, but every gust scatters that heat away, and soon the flames shrink to embers. Dry air does that to a storm. It steals the warmth before the storm can use it. Here is where it gets strange and where the forecasts break down again. Some storms survive the dry air. A storm that is already strong and tightly wound can wall itself off, sealing its core away from the dry air like a fortress slamming its gates. That storm shrugs off the poison and keeps growing. A weaker, sloppier storm, hit by the very same dry air, falls apart completely. Same poison, two completely different endings, and often the only difference is how organised the storm happened to be at the exact moment the dry air struck. This is the maddening part for forecasters. Whether a storm survives its brush with dry air can come down to timing measured in hours and to the storm's inner shape, which is one of the hardest things of all to see and to predict. A model might expect the dry air to kill a storm, and instead the storm powers straight through it. or the model expects the storm to survive and it chokes and dies. Either way, the forecast busts, so now the picture is filling in. Warm water gives the fuel, low shear clears the way, wet air lets the storm breathe. Line up all three, and a storm has its chance. Yet even with everything in place, forecasters still cannot promise a storm will explode. Something inside the storm itself has to pull the trigger. And scientists have finally caught that trigger in the act. Deep in the heart of the most dangerous storms, right before they detonate, a special kind of thunderstorm rises up out of the core. It is tall and violent, and when forecasters spot one, they know the beast is about to wake. They call these towers by a fitting name, and the sight of them means strength is coming fast. Right before a storm explodes, a single tower of cloud shoots up out of its centre, taller than any mountain on Earth. For a long time, forecasters could see all the outside ingredients: warm water, low shear, wet air, yet they still could not say which storm would suddenly leap in strength. The final clue was hiding inside the storm, in a burst of fury so tall it punches through the top of the sky. Scientists call these giants hot towers, and they are the fingerprint of a storm about to detonate. A hot tower is a single, monstrous thunderstorm. Inside a hurricane, warm air is always rising, but every so often in one spot near the centre, the rising air surges upward all at once, with incredible force. It builds a thunderstorm that climbs and climbs, far higher than the clouds around it, blasting straight up toward the edge of space. These towers reach heights of 10 miles or more, taller than a passenger jet flies. So tall their frozen tops brush the calm layer of air that sits above all our weather. The tops grow colder than almost anything in nature, far colder than the deepest freezer. The tower matters because of what it carries. All that violently rising air is dumping a colossal amount of heat into the heart of the storm, all at once. That heat is the storm's fuel, released in a sudden concentrated blast right where it does the most damage. The storm answers by spinning faster and dropping its pressure, and the winds surge in response. Where a hot tower rises, rapid intensification usually follows. Think of the storm as an engine idling quietly, ticking over. A hot tower is someone flooring the accelerator. The engine roars, the whole machine lunges forward, and the storm jumps to a new and higher gear in a matter of hours. This discovery changed how forecasters watch storms. Now, when they study the satellite loops, they hunt for these towers erupting near the core. A single tall tower blasting up from the centre is a red flag waving. It whispers that the storm is about to gain strength fast, sometimes before any other sign appears. It buys forecasters a few precious hours of warning, and in this game, a few hours can save a city. Yet even the hot tower did not solve the whole puzzle. For years, scientists believed a storm needed near-perfect conditions to blow up. Calm upper winds, a storm standing tall and straight, everything neat and balanced, that was the rule. A messy, tilted, sheared storm was supposed to stay weak, its tower knocked sideways before it could do its work. Then storms started breaking that rule too. Scientists began spotting hurricanes that exploded in strength, while leaning, while battered by shear, while looking like they had no business growing at all. By every rule in the book, these storms should have fizzled. Instead, they found a hidden back door to power, a second and stranger way to intensify that no one saw coming. And understanding that secret second path meant admitting a hard truth. The rules forecasters trusted for decades were only half the story. A leaning, battered storm, one that every rule says should die, can secretly reach for power through a hidden back door. The old rulebook was clear. To grow strong, a hurricane had to stand tall and straight, perfectly balanced, sheltered from the shearing winds up high. A storm knocked sideways was a storm on its way to dying. So when forecasters saw a tilted, messy storm getting battered by shear, they relaxed. This one, they figured, would stay weak. Then the messy storm started blowing up anyway. Scientists dug into the data and found something they had missed for years. There are actually two different ways a storm can suddenly gain strength. The first is the clean one everyone knew, the tall, straight tower over warm water. The second is far weirder, and it happens in exactly the conditions where a storm is supposed to fail. The second path works in a strange way. In a tilted, sheared storm, giant thunderstorms sometimes fire off far from the centre, out in the lopsided edges where the storm is a mess. By the old rulebook, Those distant bursts should mean nothing. Instead, they can trigger a total rearrangement of the storm. The whole spinning system shifts and reorganizes itself around the new bursts of energy. In a matter of hours, a shapeless, leaning storm can pull itself together and jump to hurricane strength, seemingly out of nowhere. Picture a marching band scattered across a field, out of step, drifting in every direction, about to fall into chaos. Then a drumbeat starts up from one corner. One by one, the players lock onto the beat, fall into formation, and suddenly the whole band is moving as one powerful unified force. That is the second mode. The storm looks scattered and doomed, then a burst of energy off to one side pulls the whole system into line, and it surges to life. This is the nightmare scenario for a forecaster. The first kind of rapid growth at least happens when conditions look dangerous, when the water is warm and the sky is calm. A watchful scientist can see it coming. But the second kind strikes when everything looks safe, when the storm is a sheared, tilted wreck that the models have already written off. It is the sneak attack, the storm that explodes at the exact moment nobody is bracing for it. And it explains some of the great forecast disasters. A storm that should have stayed weak, sitting under winds that should have torn it apart, instead found the hidden back door and roared to life. The models, following the old rules, never saw it. The warning came too late, or never came at all. So the truth turned out to be humbling. A storm can grow strong the neat way or the messy way. It can blow up when the sky is calm, and it can blow up when the sky is fighting it. Forecasters have to watch for both, which means they can never fully relax, not even when a storm looks beaten and finished. All of this power, both the clean path and the secret one, comes down to one place inside the storm. A single ring where the wind screams loudest, the rain falls hardest, and the storm's true strength lives. Everything we have talked about, the fuel and the shear and the towers, all of it builds toward this one violent ring. Fly into a hurricane, and this ring is the thing that could tear your aircraft to pieces. At the center of the worst storms on Earth lies a circle of perfect calm, ringed by the most violent wind in nature. Every powerful hurricane has the same strange shape at its heart. In the very middle sits the eye, a round pocket of quiet air. Inside the eye, the wind falls still. The rain stops. Sometimes the clouds part and you can see blue sky straight overhead or stars at night. Sailors caught inside the eye have described an eerie, dreamlike calm. The sea still wild beneath them, but the air suddenly silent as if the storm were holding its breath. Then comes the wall. Around that calm eye stands a towering ring of thunderstorms called the eye wall. This ring holds the strongest winds and the heaviest rain in the entire storm. The eye wall is where a hurricane keeps its fury. Step from the calm eye into the eye wall, and you go from dead silence to winds that can strip the bark off trees and send roofing tiles flying like knives. The calm and the chaos sit side by side, separated by a wall of screaming cloud. Here is the secret that forecasters read. The size of the eye tells you how strong the storm is. A wide, ragged, fuzzy eye usually means a weaker, sloppier storm. But a small, round, sharply cut eye, a tiny dark dot on the satellite, means a beast. The tighter the eye, the faster the winds spin around it. The reason is the same trick a figure skater uses. When a skater pulls her arms in close, she spins faster. When she spreads them out, she slows. A hurricane spins around its eye the same way. When the storm draws its power into a small, tight ring, the winds whip around that narrow center at terrifying speed. A pinhole eye, small enough to look like a single dot from space, is the mark of a truly monstrous storm. Inside the eye wall, the numbers turn extreme. The winds in the strongest storms scream past 200 miles per hour, faster than a race car at full throttle. The air here is a blur of rain, sea spray, and flying debris, all whirling around at highway speeds and beyond. It is, quite simply, one of the most dangerous places on the planet. And yet the eye wall keeps changing. It is alive, always shifting. This is where the storm plays its most confusing trick of all, the move that has ruined more forecasts than almost anything else. Because sometimes, while forecasters watch, a second wall begins to form. A new ring of thunderstorms rises up outside the first one, wrapping around the original eye wall like a larger circle drawn around a smaller one. Two walls now spin around the same eye, and only one can survive. What happens next sends the storm's strength lurching up and down in ways that leave even the best models guessing. The storm is about to rebuild itself from the inside out. And for a few strange hours, no one can say whether it will come out weaker or far, far stronger. While forecasters watch, a hurricane can tear down its own core and build a new one, and no model can perfectly predict what comes out the other side. We just saw the eye wall, the violent ring of storms around the calm eye. In the strongest hurricanes, that ring sometimes decides to replace itself. A brand new ring of thunderstorms forms out beyond the old one, a bigger circle wrapping around the first. For a while, the storm has two eye walls at once, an inner ring and an outer ring, both spinning around the same centre. Two rings cannot last. They compete. The outer ring slowly chokes the inner one, stealing its supply of warm, wet air. Starved, the inner eye wall withers and collapses. As it falls apart, the storm's winds ease off. For a few hours, a raging hurricane can actually seem to calm down, its top winds dropping, its tight little eye fading away. A coastal town watching the news might feel a flash of relief. The monster looks like it is losing steam. That relief is a trap, because the outer ring is now taking over as the new eye wall. It tightens, it contracts, shrinking inward around the eye, and as it draws in close and tight, the winds spin up all over again, faster and faster around the shrinking centre. The storm reloads. Often it comes back just as strong as before, sometimes stronger, and almost always wider, which means it can batter a much larger stretch of coast. What looked like a storm falling apart was really a storm catching its breath. Picture a boxer between rounds. For a moment he sags on his stool, exhausted, looking beaten. Then the bell rings, and he comes off that stool swinging harder than ever. The eye wall replacement is that pause between rounds. The storm that seems to weaken is often just reloading its fist. This is one of the great headaches of forecasting. During an eye wall replacement, a storm's strength swings up and down in ways that are fiendishly hard to predict. Will the new eye wall snap into place quickly and send the winds roaring back? Or will the storm stumble and stay weaker? The timing can change everything, and it can shift the peak strength of the storm right at the worst possible moment, just as it nears the coast. Even the finest models throw up their hands and guess, and these swings happen fast. The whole cycle, tearing down one eye wall and building another, can play out in less than a day. A storm can look like it is fading in the afternoon and come back as a full monster by dawn. So a hurricane is a shapeshifter. It grows, it weakens, it rebuilds, it surges again, all while marching toward land. Every stage hides a fresh way to fool the people trying to predict it. Now take everything we have seen. The deep warm water, the calm upper winds, the hot towers firing, a storm that stands tall and reorganizes and reloads its eye wall, over and over, with nothing in its way. Push all of it to the absolute limit at once, and you get the fastest, most violent strengthening ever witnessed by human beings. It happened over the Pacific in a single day, to a storm that went from harmless to history in the time it takes to sleep, eat, and sleep again. In October, off the Pacific coast of Mexico, a storm named Patricia did something no hurricane had ever been recorded doing before. It started as an ordinary storm. On one afternoon, Patricia was a modest hurricane, the kind that forms in that ocean all the time, with winds that would rattle windows and little more. Forecasters expected it to strengthen. Storms in that warm water usually do. What no one expected was the sheer speed of what came next. Everything lined up at once. The ocean beneath Patricia was blazing hot and warm to great depth, a bottomless tank of fuel. The winds up high went dead calm, almost no shear at all. The storm stood perfectly straight and began pulling that deep heat upward as fast as it possibly could. Hot towers blasted through its core. The pressure at its centre began to fall, and then to plunge. Then it went berserk. In about a single day, Patricia's winds climbed from around 85 miles per hour to over 200. It leapt from a low, ordinary hurricane all the way to the highest, most violent category, and kept going past even that. This was the fastest strengthening ever measured in that part of the world. A storm that could have been walked through in the morning had become, by the next day, one of the most powerful hurricanes ever seen on Earth. To picture that speed, imagine a storm gaining more than 100 miles per hour of wind while you slept a single night. You go to bed with a strong breeze outside. You wake up to winds that could flip a truck and flatten a house. That is what Patricia did. in roughly the span of one long sleep. At its peak, Patricia's winds screamed near 215 miles per hour, faster than the top speed of most race cars. Its central pressure dropped to the lowest ever reliably measured anywhere in the western half of the planet. For a few hours, this storm was very likely the strongest hurricane in recorded history, a swirling giant sitting just off a coastline lined with towns and cities. The world got extraordinarily lucky. Patricia hit a stretch of the Mexican coast with mountains close to shore, and rugged land tears storms apart quickly. It also eased off a little right before landfall and came in over a less crowded area. The damage, while serious, fell far short of the nightmare that a storm that strong could have caused. Had Patricia struck a major city at full strength, the disaster would have been almost beyond imagining. Patricia showed the world the raw ceiling of what these storms can do when every ingredient lines up perfectly. It was a demonstration of pure physical extremes, the atmosphere showing off the very top of its power. But Patricia, for all its fury, gave forecasters something to work with. It strengthened out over open water with time to warn people. The truly cruel storms are the ones that pull the same trick right at the coastline, in the final hours, when there is no time left to run. And a few years later, one did exactly that, to a city that never saw it coming, with a human cost that shook forecasters to their core. A city of nearly 1 million people went to sleep expecting a rainy night, and woke up in the middle of one of the strongest storms ever to hit that coast. The storm was named Otis, and at first it barely registered. Sitting off the Pacific coast of Mexico near the beach city of Acapulco, Otis looked like a weak, disorganized system. The official forecast called for a tropical storm, maybe a low-end hurricane at worst. People in the city glanced at the news, shrugged, and made ordinary plans. A little wind, some rain, nothing to flee from. The models were about to be catastrophically wrong. Overnight, Otis found everything it needed. The water beneath it ran warm and deep. The upper winds fell quiet, and the storm, so recently a shapeless mess, pulled itself together and detonated. In the span of a single night, Otis exploded from a middling storm into a top-category monster, its winds rocketing up by more than 100 miles per hour while the city below slept. It was one of the fastest, most extreme intensifications ever recorded so close to land. There was almost no warning. By the time anyone understood what was happening, the monster was already there. Otis slammed into Acapulco in the dark early hours as a full, screaming top-category hurricane. Skyscrapers along the beachfront had their windows blown out and their walls torn open. Neighborhoods were flattened. Power and phones went dead across the whole region. When the sun rose, a famous resort city lay in ruins, cut off from the outside world. Dozens of people lost their lives, and the damage climbed into the billions. This became one of the most painful forecast misses in modern history. Everyone wanted to know how the models could have been so wrong. The answer is everything we have talked about. Otis intensified in one of those hidden, hard-to-see ways. Over deep, warm water, the models underestimated, pulling its power together fast in the dark right at the coast. The storm did the exact thing that forecasting still cannot reliably catch. It exploded at the worst possible place and the worst possible time, in the final hours, when a wrong forecast cost the most. Picture the difference in warning. A slow storm gives a city days to empty out, to board windows, to move families inland. Otis gave Acapulco a few hours in the middle of the night, with a forecast that said there was little to fear. By the time the truth was clear, the roads were already too dangerous to travel. The window to escape had slammed shut before anyone knew it had opened. Otis is the reason this problem reaches far beyond a science puzzle. It is a matter of life and death. Every hour of warning that forecasters can win back is a chance for more people to reach safety before the winds arrive. That is what drives the scientists chasing these storms, and it drives them to do something that sounds insane. To learn what a storm is truly doing inside, where satellites cannot see and models can only guess. A handful of brave crews climb into airplanes and fly straight into the heart of the beast. While most people flee from a hurricane, a small group of pilots points their plane directly at the eye and flies in. They are called the hurricane hunters, and their job sounds impossible. When a dangerous storm churns over the ocean, they load up a sturdy airplane packed with instruments and fly it straight into the storm, into the rain, into the wind, through the screaming eye wall itself, the most violent ring in the whole hurricane, and out into the strange calm of the eye. Then they turn around and do it again. crisscrossing the storm to map it from the inside. The flight through the eye wall is brutal. As the plane punches into the wall of thunderstorms, the ride turns savage. The aircraft slams up and down in the churning air, dropping and lurching, rain hammering the windows, everything shaking so hard the crew can barely read their screens. It is like driving a car at full speed over a field of boulders, in the dark inside a car wash. The pilots fight the controls to keep the plane level while nature does its best to throw it around the sky. Then suddenly everything goes quiet. The plane bursts through the inner edge of the eye wall and into the eye. The shaking stops. The rain vanishes. Above them, sometimes, is clear blue sky or a field of stars, and all around them stands a towering circular wall of cloud, like being inside a giant open-air stadium made of storm. Crews describe it as one of the most beautiful and haunting sights in all of nature. For a few minutes, they float in the calm heart of a monster. Why risk it? Because there are things about a storm that no satellite can ever measure. From space, we see the storms outside, its clouds and its shape and its temperature from above. But the real action, the pressure at the center, the exact wind speeds, the moisture deep inside, all of that lives down in the storm where satellites cannot reach. The only way to truly know those numbers is to go there and measure them directly. The hurricane hunters carry instruments that read the storm from the inside, and they beam that information back to the forecasters on the ground in real time. That direct data is gold. When a hurricane hunter flight sends back the true pressure and the true winds at the core, the forecast gets sharper, sometimes dramatically. The plane can catch a storm strengthening hours before a satellite would notice, giving coastal towns a little more of that precious warning time. Some of the biggest improvements in storm forecasting have come straight from these flights into the beast. And the crews do more than measure the air around the plane. They carry a special tool, small and clever, that lets them reach into parts of the storm the plane itself never touches. As they fly across the hurricane, they drop these little devices out of the aircraft and let them fall. Each one tumbles down through the storm, all the way toward the raging sea, sending back a stream of secrets the whole way down, and what those falling tubes reveal has cracked open some of the storm's deepest mysteries. Falling through the heart of a hurricane, a tube no bigger than a paper towel roll is quietly stealing the storm's deepest secrets. The hurricane hunter crews call these little devices dropsons. Each one is a slim tube stuffed with tiny sensors and a small radio. As the plane flies across the top of the storm, the crew releases the dropsons one by one, and a small parachute pops open to slow the fall. Then the tube drifts down through the entire storm, from the high-flying plane all the way to the surface of the sea. The whole way down it is listening to the hurricane. As it falls, the dropson measures everything around it, the pressure of the air, the temperature, how much moisture is in the air, how fast and which way the wind is blowing, and it measures all of this again and again at every level, from the top of the storm down to the waves. Every second or two it radios a fresh reading back up to the plane. In a couple of minutes, a single falling tube paints a complete top-to-bottom picture of one slice of the hurricane. This is the part satellites can never do. A satellite floating in space sees the storm from above, like looking down at the roof of a house. It can tell you the shape of the roof and how cold the top of it is, but it stays stuck outside. It cannot walk down the stairs and check every floor. The dropsond is that walk through the house. It reads the storm floor by floor, all the way to the basement where the wind meets the water, revealing the hidden inner structure that decides whether a storm will grow or fade. Picture trying to understand a tall building by only ever looking at it from a helicopter far overhead. You would see the rooftop and nothing else. Now imagine you could drop a sensor down through the middle of the building that reported back the temperature and conditions on every single floor as it fell. Suddenly you know the building inside and out. That is what a dropson does to a hurricane. These readings feed straight into the forecast models, and they matter enormously. When forecasters know the true, detailed guts of a storm, their predictions of its strength improve. The dropson can catch the early signs of rapid intensification, spotting the falling pressure and the shifting winds deep inside before those changes ever show up anywhere else. Each little tube costs a fair bit of money and is used only once, tumbling into the sea when its job is done. Yet the information it sends back is worth far more than the device itself. Between the hurricane hunter planes and their falling dropsons, Scientists have pried open much of the storm. They can now read the pressure, the winds, the moisture, the towers, almost the entire machine. Almost. Because there remains one thin slice of the storm that all our cleverness still cannot reach. It is the most important region of all, the exact place where the hurricane draws its power from the sea, and it may be the single hardest place on Earth to measure. Right where the wind meets the water, our instruments go blind. The most important place in a hurricane is a layer so thin and so violent that no one has ever truly measured it. We have flown planes into the eye. We have dropped sensors through the storm from top to bottom. Yet one region still defeats us, and it happens to be the region that matters most. It is the boundary where the bottom of the storm meets the top of the sea, a churning, chaotic zone only a small distance thick, right down at the surface of the water. This thin layer is where a hurricane feeds. Everything a storm does begins here, in this narrow band where warm ocean touches hungry air. This is where the heat leaves the sea and enters the storm. This is where the fuel transfers, where the whole engine takes its first breath. Get this layer right, and you can understand how fast a storm will grow. Get it wrong, and the entire forecast wobbles. The most powerful hurricanes are the ones that pull heat across this boundary the fastest, and it is nearly impossible to study. Down in this zone, during a real hurricane, the world is pure chaos. The wind is screaming past 200 miles per hour. The sea churns into something wild. It is torn apart into a blinding froth of spray and foam and airborne water, the ocean and the sky blended into a single wild soup. No instrument survives long in that violence. No boat can sit there. Even the dropsons, so brilliant everywhere else, are falling too fast and hitting too much chaos to fully capture what happens in this final, crucial slice. Picture trying to measure the exact temperature and speed of the water inside a giant blender while it is running at full power, without being able to open the lid or put anything inside. That is the challenge. The thing scientists most need to measure is the thing hardest to reach, hidden inside the most violent conditions on the planet, and scientists cannot easily fake it either. In their labs, they try to recreate this froth of spray and wind, hoping to learn how much heat crosses that boundary at extreme wind speeds. But building those monstrous conditions on purpose is enormously difficult. So a huge question mark sits right at the core of every storm forecast. Exactly how fast does the heat move from sea to storm when the winds go wild? Nobody fully knows. This gap is one reason storms still surprise us. A model has to guess what is happening in that blurry boiling layer, and if its guess is off, its forecast of the storm's strength can be off too. The very foundation of the storm, the place where it draws its life, remains partly a mystery. So far, every wall we have hit has been a practical one, a layer too violent to measure, warm water too deep to see. If only we had better tools, we tell ourselves, we could crack it. Build a tougher sensor, launch a sharper satellite, and the storm would finally give up its secrets. But the next wall is different, and far stranger. It is a limit built into the very nature of weather itself, a barrier that would stop us even if our instruments were perfect. There is a point beyond which no one can ever see, and a single flap of a butterfly's wings helped scientists discover it. In the early days of computer weather forecasting, a scientist typed one tiny number into his machine, and by accident discovered why the future can never be fully known. His name was Edward Lorenz, and he was running one of the first computer weather models. One day he wanted to repeat a forecast, so he typed in the numbers from an earlier run to start it over. To save time, he rounded one number, chopping off a few tiny decimal places at the end. The change was almost nothing, a difference smaller than a speck, the kind you would never think could matter. Then he watched the forecast go completely insane. The new run started out matching the old one, but slowly the two forecasts drifted apart. Then they split wildly, until they described two totally different weathers, one calm, one stormy, born from numbers that were nearly identical. That microscopic rounding, that hair of a difference, had grown into a total disagreement. Lorenz sat back, stunned. He had stumbled onto one of the deepest truths in all of science. The atmosphere is what scientists call chaotic. In a chaotic system, the tiniest change at the start snowballs into an enormous change later on. A puff of air today, too small to feel, can decide whether a storm forms next week. People gave it a famous nickname, the butterfly effect. The idea that a butterfly flapping its wings in one part of the world could, through a long chain of tiny nudges, help stir up a storm on the far side of the planet. Picture a pinball machine. You pull the plunger and launch the ball. Pull it back the same way twice, almost, with the tiniest difference in force, and the ball ricochets down two completely different paths, bouncing off different bumpers, ending up somewhere else entirely. The atmosphere is that pinball machine, and every storm is the ball. A hair of difference at the launch sends everything down a new road. This is why weather forecasts get shakier the further out they reach. Tomorrow, the tiny errors have not had time to grow, so the forecast is sharp. A week out, those errors have snowballed and the forecast gets fuzzy. Push far enough and the errors swamp everything. Scientists believe there is a hard ceiling, somewhere around 2 weeks, past which day by day weather simply cannot be predicted, no matter how good our computers get. The chaos wins, and this is a different kind of a wall than the ones we hit before. Better instruments cannot fix it. A sharper satellite cannot fix it. The limit lives in the nature of the atmosphere itself. Even if we measured every speck of air on Earth perfectly, the tiny gaps between our measurements would still snowball, and the future would still slip away. So forecasters faced a hard question. If a single forecast can be thrown off by something as small as a butterfly, how can you ever trust just one? The answer they came up with is clever, and a little bit wild. If you cannot trust one forecast, you stop making one. You make 100 of them at once, each one slightly different, and you let them show you every future the storm might choose. Instead of making one forecast and hoping it is right, forecasters now make dozens of them at once, on purpose. The idea flows straight out of the butterfly effect. Since the tiniest change at the start can send a forecast down a wildly different path, scientists decided to lean into that fact. They take the storm and run it through the computer many times over. Each run starts with the conditions nudged a tiny bit differently. A little more moisture here, a slightly stronger wind there, small changes, the size of the errors that always sneak into our measurements. Then they let all those versions play out and see where each one ends up. This collection of runs has a name. Scientists call it an ensemble. Here is what makes it powerful. When all the runs agree, when every version of the storm heads for the same coast and grows to about the same strength, forecasters can trust the forecast. The chaos did not have much room to change things this time, but when the runs scatter, when one sends the storm out to sea and another slams it into a city, the forecasters know they are dealing with a jittery, unpredictable situation. The spread of the runs measures how confident they can be. Picture 100 archers all aiming at the same distant target. Each looses an arrow, and because no two shots are ever perfectly identical, the arrows scatter a little across the board. If they all cluster into one tight group, you can trust the aim, but if the arrows spray across the whole target, left and right and high and low, you know the shot is deeply uncertain. Forecasters read a storm's future the same way, by watching how tightly their runs cluster. The number of runs is impressive. A modern ensemble can include 50 different versions of the future, or even more, all computed at once on giant supercomputers, all for the same single storm. It is like sending 50 scouts down 50 slightly different roads to report back on what they find. Together they map out the range of everything that could happen. This changed forecasting in a deep way. Rather than pretending they can pin down the one true future, scientists now embrace the uncertainty and measure it head-on. They can tell a coastal town not just where a storm might go, but how sure they are about it. And that honesty saves lives, because it tells people when to take a threat seriously, even if the most likely path misses them. The ensemble also catches the dangerous surprises. Sometimes, out of 50 runs, a handful show the storm doing something extreme, rapidly intensifying right before landfall. Even if most runs stay calm, those few alarming ones are a warning. They say this storm has it in her. Under the right nudge, she could explode. Forecasters have learned to respect those outliers, because reality sometimes follows the scary path. So now scientists had a way to see many futures at once. The next problem was how to look at all of them together without drowning in numbers. They needed a picture, a single image that could show 50 different storms on one map. And when they drew it, the result looked so tangled and messy that people started calling it after a plate of noodles. Turn on the news during a hurricane, and you will see a map covered in a tangle of coloured lines, spreading out from the storm like a fistful of thrown noodles. People started calling these maps spaghetti models, and the nickname stuck for an obvious reason. Each line on the map is one prediction of where the storm will go. Some lines come from the many runs of an ensemble. Others come from different forecasting systems around the world. Draw them all on one map at the same time, and you get a snarl of lines curving and crossing and fanning out across the ocean, exactly like spaghetti dumped on a plate. But the tangle is telling you something important. Look at how the lines are spread. When they all bunch together into a tight, neat bundle, pointing the same way, that is good news for forecasters. It means the different predictions agree. The storm's path is fairly certain. Everyone should get ready in the same place. But when the lines spray apart, some going left, some going right, some curving out to sea, that fan of disagreement is a warning. The storm's future is wide open, and a huge stretch of coast has to stay alert. Picture 2 handfuls of spaghetti. Toss the first handful, and it lands in a tidy line, all the noodles pointing roughly the same direction. Toss the second, and it scatters everywhere, noodles flying left and right. The first is a confident forecast. The second is a coin flip. One glance at how tangled the lines are tells you how nervous the forecasters should be. Here is where people often get it wrong, though. Many folks stare at the spaghetti map hunting for their own town, trying to see if a single line crosses right over their house. That is a mistake. No single line is a promise. Each line simply shows one possible path among many, and together they reveal the whole spread of what might happen, so you can judge the odds. A town sitting in the thick of the bundle is in real danger. A town off to the side, brushed by only one stray line, faces a smaller but real chance. And there is a deeper puzzle hiding in those lines. Some of them do more than show slightly nudged versions of the same forecast. Some come from entirely separate weather computers, built by different countries running on different math. And here is the strange thing. When you feed these separate computers the very same storm, the very same starting conditions, they can still disagree. One might predict a monster, another might predict a dud. Same storm, same ocean, same day, 2 different answers. That should not happen if the science was simple. Both computers are running the laws of physics, the same rules of air and water and heat. So why would they ever come to different conclusions about the same storm? The answer reveals just how hard this problem really is, and why forecasting a storm's strength remains one of the great unsolved challenges in all of science. 2 of the most powerful supercomputers on Earth can look at the exact same storm and see 2 completely different futures, and the reason hides in a problem no computer can escape. Both machines are running the laws of physics, the same rules of heat, air and water that govern every storm. In a perfect world, feeding them the same storm would give the same answer every time, yet they disagree, sometimes dramatically. To see why, you have to understand how a weather computer actually thinks. A computer cannot track every single molecule of air. There are far too many. So instead, it chops the whole atmosphere into a giant grid of boxes, like slicing the sky into a 3-dimensional checkerboard. It calculates the weather in each box, then figures out how the boxes affect their neighbours. The smaller the boxes, the sharper the forecast. But even the best models use boxes several miles wide, because smaller boxes mean far more calculations. And even supercomputers have their limits. Here is the trouble. Some of the most important things a storm does happen inside a single box, at a scale smaller than the grid can see. A towering thunderstorm, a swirl of the eye wall, the exact churn where wind meets water. The computer cannot draw these directly. They are too small, so it uses a shortcut, a set of clever rules that estimate what is probably happening down at that tiny scale, based on the conditions in the box. And this is where the computers split apart. Different modelling teams write those shortcut rules differently. One team estimates the small-scale storms behave one way. Another team estimates slightly differently. Both are reasonable. Both are educated. But those small differences in the rules can grow, thanks to the chaos we already met, into big differences in the final forecast. Picture 2 expert chefs handed the exact same basket of ingredients and the same recipe. One adds the salt early, cooks a touch hotter, stirs by instinct. The other salts late, cooks low and slow, follows the steps to the letter. Same ingredients, same recipe, and 2 different meals come out of the kitchen. The forecast computers are those chefs. The physics is the recipe. The tiny choices in how they handle what they cannot see directly lead them to different dishes. This is why forecasters lean on several models at once, the different chefs of the weather world, weighing their answers against each other. When the models agree, confidence rises. When they clash, the forecasters have to use judgment, experience, and gut instinct to decide which one to believe. Predicting a storm is still in part a human art. So the storm hides behind two different veils: the chaos of the atmosphere, which blurs the future no matter what, and the limits of the computers, which cannot quite capture the tiny, furious details deep inside the storm. Together they keep a storm's strength maddeningly hard to pin down. Yet even with all this uncertainty, scientists discovered something surprising. There is a ceiling. For any given patch of ocean, on any given day, the laws of physics set an absolute top speed that a storm cannot pass. A hard limit, written into nature, or so they believed. Because a few storms have come along and shattered that ceiling, reaching strengths the rules said should be impossible. Every hurricane has a speed limit it should never be able to break, and the ocean itself sets the number. Decades ago, a scientist named Kerry Emanuel worked out the math behind a storm's raw power. He treated a hurricane like the heat engine it truly is, a machine that turns ocean warmth into wind. And like any engine, it has a maximum. There is only so much energy in the warm water below and the cool air above, and physics decides how much of that energy a storm can turn into spinning wind. Push a storm to use every last bit and you reach its ceiling. Emanuel called this the maximum potential intensity, the absolute strongest a storm could ever get given the conditions around it. Think of it like a level cap in a video game. No matter how long you play, how many points you rack up, your character cannot climb past the top level the game allows. The maximum potential intensity is the storm's level cap. The winds simply cannot go higher than the cap for that patch of ocean that day. Here is the part that should worry us. The cap can move, and the single biggest thing that moves it is the temperature of the sea. Warmer water raises the cap, cooler water lowers it. Over a cold ocean the cap sits low, and even a healthy storm can only get so strong. Over blistering hot water the cap climbs, and a storm has room to grow into a true monster before it hits the ceiling. This gave forecasters a powerful tool. By measuring the ocean and the air, they can calculate the cap for any storm anywhere. They can look at a hurricane and say, the most this thing could ever become is right here at this number. It draws a line on the storm's ambitions. Most hurricanes never even reach their cap. Dry air, wind shear, and their own messy structure hold them back, so they top out well short of the ceiling nature would allow. But the caps themselves are climbing. As the oceans warm year after year, the maximum potential intensity in many regions is creeping upward. The ceiling that once held storms to a certain strength is rising, giving future storms permission to grow stronger than the storms of the past. The theoretical monster of today would have been impossible over the cooler seas of a century ago. For a long time, this ceiling seemed rock solid. It was the one rule you could count on. A storm might surprise you by growing faster than expected, or turning where you did not predict, but it would never break through its physical maximum. The cap was the law, the final word on how bad things could get, and then a handful of storms did the impossible. Careful measurements caught certain hurricanes spinning with winds that reached above the ceiling the theory set for them, storms that, on paper, should not have been able to get that strong. They had broken through their own level cap, and scientists were left scrambling to explain how a storm could shatter a limit written into the laws of physics. A storm breaking through its own speed limit sounds impossible, yet the measurements keep showing it happen. The maximum potential intensity is supposed to be a wall, the strongest a storm can physically become. So when hurricanes turn up with winds pushing past that wall, it is like finding a student who scored above 100% on a test. The number should not exist, and yet, again and again, a few storms manage it, spinning harder than the theory says the ocean and air could ever allow. How? Scientists have a few ideas, and the truth is probably a mix of them. One answer is that the ceiling is an average, not a hard fence. The theory describes the strength a storm can hold steady over time, in balance with its surroundings. But a storm in the throes of rapid intensification runs wild and out of balance. It is a runaway engine, briefly overshooting, like a sprinter who bursts past their sustainable pace for a few furious seconds before their body forces them back down. A storm can punch above its ceiling for a short window, then settle back below it. Another answer is that the storm creates its own conditions. A truly intense hurricane can reach up and change the air high above it, warming and drying the upper atmosphere in a way that lifts its own ceiling. The storm, in effect, raises the cap by its own fury, then climbs into the new space it made. It bootstraps itself higher, pulling on its own laces, and part of the answer is simply that measuring a storm's true peak winds is incredibly hard. The strongest gusts happen in tiny fleeting patches inside the eye wall, in conditions too violent to measure cleanly. So some of these limit-breaking numbers may sit at the very edge of what our instruments can even trust. The storm and the ruler are both a little uncertain at the extremes. Whatever the reason, the lesson is humbling. Even our best theory of a storm's power, one of the proudest achievements in the science, turns out to have soft edges. Nature keeps finding cracks in the rules we write for it. Every time scientists draw a firm line and say a storm can go this far and no farther, some storm somewhere sails right past it. This is the heart of why these storms fascinate and frighten us. They live at the ragged edge of what we understand. They obey our rules most of the time, enough for us to feel we have them figured out, and then one of them breaks free and reminds us how much we still do not know. And here is a pattern worth noticing. So many of these rule breakers, the fastest intensifiers, the limit smashers, the forecast wreckers, share the same birthplace. They come roaring out of one particular ocean, a stretch of sea that seems almost designed to build impossible storms. The Eastern Pacific off the coast of Mexico and Central America is a factory for monsters. And to understand why, we have to look at what makes this one patch of ocean so uniquely, dangerously perfect. One stretch of ocean off the coast of Mexico builds more monster storms faster than almost anywhere else on Earth, and its secret is a nearly perfect recipe. The Eastern Pacific, the warm water west of Mexico and Central America, has everything a growing storm could dream of. Start with the sea itself. It runs hot, often well past that 80-degree line, and the warmth reaches down deep, a fat reserve of fuel waiting below the surface. Storms that form here are sitting on top of an enormous tank of energy from the moment they are born. Next comes the calm above. Compared to many other storm basins, the Eastern Pacific often has gentle upper winds, low wind shear, the very condition that lets a storm stand tall and grow. The knife in the sky that shreds so many storms elsewhere is frequently missing here. The storms get to build straight up, undisturbed, reaching for their full strength. Then there is the geography. In this basin, storms often form close to shore and quickly wander out over open, warm water, away from land. Land is a storm killer, rough ground that tears a hurricane apart. But Eastern Pacific storms frequently get long, clear runs across nothing but warm sea, with plenty of room and time to explode before anything slows them down. Put it all together, and you have a greenhouse for hurricanes. A greenhouse works because it controls everything a plant needs: the warmth, the moisture, the shelter, and tunes it all for fast growth. The Eastern Pacific does the same for storms: warm deep water for fuel, calm winds for shelter, open ocean for room to run. It is a space tuned, almost perfectly, to grow storms fast. This is why so many of the record breakers were born here. The fastest intensifier ever measured spun up in these waters. The storm that shattered the pressure record formed here too. Time and again, when a hurricane does something that leaves scientists slack-jawed, you can trace it back to this same slice of the Pacific. This basin specializes in overachievers, and the storms here get less attention than they should. Many of them spin far out over the ocean and never touch land, so the wider world barely hears about them. A hurricane can reach the top category in the Eastern Pacific, a genuine giant, and make almost no news, because it threatens only open water and a few ships. These quiet monsters give scientists a priceless laboratory, a place to watch extreme storms do their worst without a city paying the price. But this perfect storm factory does not always run at the same speed. Some years it roars, pumping out one powerful hurricane after another. Other years it goes quiet. Something flips the basin between these moods, turning the monster factory up and down like a giant dial. That dial sits in the water itself, a vast shifting pool of warmth that shows up every few years and rearranges storms across the entire planet. When it appears, the Eastern Pacific catches fire, and oceans on the other side of the world fall strangely calm. Every few years, a giant pool of warm water spreads across the Pacific, and when it does, it rewrites the rules of storms around the whole planet. Scientists call this warming El Niño. Normally, the waters of the central and eastern Pacific sit at their usual temperature. But every so often, for reasons tied to shifting winds and currents, that huge stretch of ocean heats up, sometimes by several degrees. It sounds small. A few degrees across a vast ocean changes weather across entire continents. For the Eastern Pacific Storm Factory, El Niño is a massive boost. The extra warm water raises the fuel supply, and the shifting winds calm the upper air, dropping the wind shear even lower than usual. The basin, already good at building monsters, goes into overdrive. During strong El Niño years, the Eastern Pacific can churn out an unusual number of powerful hurricanes, one after another. Now here is the strange part. While El Niño supercharges the Pacific, it does the opposite on the other side of the continent. Over in the Atlantic, the same El Niño cranks the wind shear up, filling the sky with the very winds that rip storms apart. So Atlantic hurricanes get choked off in the same season that Pacific ones run wild. Picture a giant seesaw stretched across the whole hemisphere. When El Niño pushes the Pacific side up, alive with storms, the Atlantic side drops down, quiet and calm. When El Niño fades, the seesaw tilts back the other way. One warm pool of water, sitting in the middle of the Pacific, controls the balance of storms across two entire oceans. Few things show off the connected nature of our planet's weather more clearly. And right now, the seesaw is tilting hard. Forecasters are watching a powerful El Niño build in the Pacific, one that some believe could grow into one of the strongest ever recorded. The warm pool has been strengthening month after month, climbing past the levels seen in famous El Niño years of the past. If it keeps growing, the Eastern Pacific could face a season of exceptional, dangerous storms, while the Atlantic stays oddly peaceful. For the people who study these things, an El Niño like this is a rare and revealing event. It pushes the whole system toward its extremes, and extreme conditions are where scientists learn the most. They get to watch the storm factory run at full tilt, testing the very limits of how strong and how fast these hurricanes can grow. But a warm Pacific does more than spin up hurricanes far out at sea. It also loads the atmosphere with staggering amounts of moisture, and that moisture has to go somewhere. Much of it gets swept up into long, invisible ribbons of water vapor high in the sky, ribbons that stretch for thousands of miles across the ocean toward land. These ribbons are storms of a completely different kind. They carry more water than the largest river on Earth, and when one takes aim at the coast, it can drown a region in a matter of days. High above the Pacific, invisible rivers of water float through the sky, each one carrying more water than the mightiest river on the ground. They are called atmospheric rivers, and the name is exact. Warm ocean air near the tropics soaks up enormous amounts of water vapor. Winds then gather that moist air into a long, narrow ribbon and send it streaming across the ocean, thousands of miles long but only a few hundred miles wide. A ribbon of concentrated water flowing through the air, aimed like a hose at a distant coast. The amount of water they carry is almost unbelievable. A single strong atmospheric river moves more water through the sky than the largest rivers on Earth carry across the land. Picture the flow of a giant river, wide and deep and endless, lifted off the ground and set floating through the air overhead. Some of these ribbons move more than twice the flow of the mightiest river on the planet. All of it invisible, all of it sailing silently toward the coast until it hits something that makes it fall. That something is usually a mountain range. When an atmospheric river slams into the mountains along a coast, the land forces all that moist air to rise. As it climbs, it cools, and the vapor turns to rain and snow dumped out in staggering amounts. A fire hose of water pointed straight at the hills. The west coast of the United States gets hammered by these events, especially in winter. A single strong atmospheric river can drop feet of rain and many feet of snow in just a few days, all in one place. These ribbons are a strange mix of blessing and curse. On the good side, they deliver much of the water the West depends on, filling the reservoirs and packing the mountains with snow that melts through the dry season. Whole regions rely on these sky rivers to survive. On the bad side, when one stalls over the same spot too long, or when several arrive back to back, the water has nowhere to go. Rivers on the ground burst their banks, hillsides give way and slide, towns flood. What waters the land one week can drown it the next, and they are fiendishly tricky to forecast. The exact strength of an atmospheric river and the exact spot where it will come ashore can shift at the last minute, thanks to the same chaos that plagues every storm. A ribbon aimed at one valley can swing and soak the next one over instead. A storm expected to be mild can arrive as a deluge. Forecasters watch them with the same nervous respect they give hurricanes, because a misjudged atmospheric river can catch a region badly off guard. So the Pacific breeds two very different kinds of rule-breaking storms. The spinning hurricanes far out at sea, and these long ribbons of water aimed at the coast. Yet the Pacific has one more trick, a third kind of monster that forms in the cold months, over the chilly northern part of the ocean. This one is born in the cold, from the violent clash of warm and frigid air, and it explodes into being almost overnight, dropping its pressure so fast that forecasters borrow a word from the world of explosives to describe it. In the cold months, over the grey northern Pacific, a storm can deepen so violently that scientists named it after a bomb. The proper name is bombogenesis, and the storms it makes are called bomb cyclones. The idea comes from the falling pressure we met earlier, the number at the heart of a storm. When that pressure drops fast enough, the storm counts as a bomb. The official cutoff is a plunge of a certain amount in just 24 hours, a nosedive in pressure that signals a storm rapidly gathering ferocious strength. These winter monsters run on a different fuel than hurricanes. A hurricane sips its energy from warm tropical water. A bomb cyclone feeds on contrast. It forms where a mass of warm air crashes up against a mass of frigid Arctic air, often along the boundary called the jet stream, the fast river of wind high in the sky. Where the warm and cold air meet and fight, the atmosphere becomes wildly unstable. The storm harvests energy from that clash, and it can grow with terrifying speed. Picture dropping a scorching hot pan straight into a sink of ice-cold water. The violent meeting of hot and cold makes the whole thing hiss, crack, and erupt. A bomb cyclone is that eruption, spread across hundreds of miles of ocean. The bigger the difference between the warm and cold air, the more explosive the storm. When one of these bombs goes off over the Pacific, the results are savage. The winds can reach hurricane strength, screaming across the open ocean. The waves they whip up are the stuff of nightmares, walls of water tall enough to tower over a house, rolling for thousands of miles. Ships caught in a Pacific bomb cyclone face some of the most dangerous seas on the planet. And when the storm swings toward land, it can slam the coast with roaring wind, flooding rain, and heavy snow, all at once. Bomb cyclones and atmospheric rivers often travel together, a deadly team. The spinning bomb cyclone acts like an engine, reaching down and grabbing one of those ribbons of tropical moisture, then flinging it at the coast with tremendous force. The bomb provides the muscle, the river provides the water. Together they can batter a coastline with a storm far worse than either could manage alone. And these storms carry the same curse as their tropical cousins. They can deepen so fast that forecasts struggle to keep up. A storm that looks moderate one evening can bomb out overnight and greet the morning as a howling giant. The rapid drop in pressure, the sudden gathering of strength, echoes the same rapid intensification that makes hurricanes so hard to predict. Fast growth, once again, is the enemy of the forecast. So across the Pacific, in every season, storms keep finding ways to surprise us. Warm season hurricanes that explode over tropical seas, winter bombs that erupt over cold water, rivers in the sky that drown the coast, all of them growing harder to predict and many of them growing stronger. Because behind all of these storms, one quiet change is at work, warming the seas, thickening the air with moisture, and slowly tilting the odds toward the extreme. The ocean is heating up, and that single fact may be rewriting the rulebook of storms faster than anyone expected. Storms are exploding in strength more often than they used to, and the numbers behind that change are hard to ignore. We already saw that warm water fuels these storms, and that the oceans have been running record hot. Now comes the consequence. As the seas have warmed over the past few decades, rapid intensification, that terrifying overnight surge in power, has been happening more and more. The storms of today blow up faster, and more often, than the storms our grandparents knew. The trend shows up clearly in the records. Scientists who dug through decades of storm data found that the number of hurricanes going from weak to monstrous in a hurry has climbed sharply. In one major ocean basin, the count of storms that rocketed from a low category up to a major hurricane more than doubled when they compared recent decades to the ones before. The most extreme intensification events, the biggest overnight leaps in wind speed, have grown noticeably more common across the globe. The pattern points the same direction almost everywhere scientists look. Warmer water is the engine behind the shift. Think of it like loading a pair of dice. In any given storm, rapid intensification was always possible, a roll of the weather that might or might not come up. But a warmer ocean quietly weights the dice, making that dangerous roll come up more often. Any single storm is still a gamble, still shaped by chaos and sheer and dry air. Yet across thousands of storms the loaded dice show their hand. The extreme outcomes pile up. This matters enormously for the people in harm's way, because rapid intensification is the exact thing that catches communities off guard. A storm that strengthens slowly gives fair warning. A storm that explodes right before landfall gives almost none. If these overnight surges keep growing more common, then more storms will arrive as nasty surprises roaring ashore stronger than anyone had time to prepare for. The very trend that scientists are tracking is the one that cost the most lives. And warmer seas do more than make storms strengthen faster. They also raise the ceiling on how strong storms can ultimately get, lifting that maximum potential intensity we talked about earlier, so the trend runs in two directions at once. More storms are reaching for their peak strength quickly, and the peak they can reach is climbing higher, faster and stronger together. Forecasters feel this change in their bones. Storms that would have been considered freak events a generation ago now show up with unsettling regularity. The record books, which used to stand for decades, get rewritten every few years. What counts as an extreme storm is shifting, and the extreme is becoming the new normal. A warmer world does more than strengthen storms. It is reshaping their entire personality, changing how much rain they drop, how fast they move, and how long they linger over a suffering town. Warming can turn even a weaker storm into a catastrophe. And one of those changes may be the most dangerous of all. The deadliest part of a modern hurricane is often the water it carries, more than the wind, and a warming world is loading storms with more water than ever. Here is the simple physics behind it. Warm air holds more moisture than cool air. Heat up the atmosphere, even a little, and it can soak up and carry noticeably more water vapour. So as the world warms, the air feeding every storm comes preloaded with extra moisture, ready to fall as rain. A hotter sky is a wetter sky. Think of the atmosphere as a sponge. A cool sponge holds only so much water. Warm that sponge and it can soak up more, swelling with extra moisture. When a storm comes along and wrings that warmer, fuller sponge out over a town, far more rain pours down. Scientists have measured this in real storms. The heaviest rainfalls are getting heavier, and warming is a big reason why. A storm today can drop noticeably more rain than the same storm would have dropped in a cooler past. Then comes a second, sneakier change. Some storms are slowing down. The winds that steer hurricanes across the globe have, in places, been growing sluggish. A storm pushed by weaker steering winds crawls forward instead of racing through. And a slow storm is a dangerous storm because it lingers. Rather than sweeping over a town in a few hours and moving on, it parks overhead and pours rain on the same spot for days. The flooding piles up with nowhere to drain. Put the two changes together, and the danger multiplies. A wetter storm that also moves slower is a recipe for catastrophic flooding. In recent years, storms have stalled over coastlines and dumped unbelievable amounts of rain, feet of water in a matter of days, swamping entire cities. Some of these floods came from storms that were not even especially strong by wind speed. They were simply wet and slow and stubborn, sitting in one place and drowning it. This flips an old assumption on its head. For a long time, people judged a hurricane mostly by its wind, by its category number. A weak storm meant a small threat, but a warming world has broken that link. Now a modest storm, low on the wind scale, can still deliver a historic disaster through rain and flooding alone. The category on the news tells you about the wind, and says far less about the water that may be the real killer. So warming is reshaping storms from every angle. It makes them intensify faster. It raises the ceiling on their peak strength. It packs them with more rain. And in places it slows them to a deadly crawl. The rulebook that forecasters spent a century writing is being edited by a changing climate, faster than the textbooks can keep up. Facing all of this, scientists could have thrown up their hands. Instead, they reached for a powerful new weapon, one that learns the storm in a completely different way than any model before it. A machine that studies the storm without ever being taught the laws of physics at all. It teaches itself, by learning from every storm that ever came before. A new kind of forecaster has arrived, one that never learned the laws of physics, yet can predict a storm faster and sometimes better than the giant machines that came before. For decades, weather computers worked one way. They took the laws of physics, the rules of air and heat and water, and calculated the atmosphere forward step by step. It was slow, careful, and demanding, requiring some of the most powerful supercomputers on Earth to grind away for hours. Now a different approach has burst onto the scene, and it thinks in a completely different way. These new systems are built on artificial intelligence. Rather than being taught the rules of weather, an artificial intelligence forecaster is shown decades of past weather, storm after storm, year after year, millions of maps of how the atmosphere actually behaved. It studies all of it, and slowly learns the patterns for itself. It figures out from sheer experience how one weather pattern tends to lead to the next. It skips the physics equations entirely, recognizing instead what usually happens, the way you learn to recognize things without thinking. Think about how you know a friend's face. You do not measure the distance between their eyes or calculate the angle of their nose. You just look and you know instantly, because you have seen that face 1,000 times. An artificial intelligence forecaster knows storms the same way. It has seen so many that it can look at today's weather and sense from deep experience what tomorrow will bring, and the results have stunned the experts. These learning systems can produce a forecast in seconds or minutes, work that used to take the old supercomputers hours. Even more surprising, their predictions have turned out to be remarkably good, matching and sometimes beating the traditional physics models at tracking where a storm will go. A tool that seemed like a gamble a few years ago now sits alongside the best forecasting systems in the world. For the hardest problem of all, predicting a storm's strength, artificial intelligence brings a special gift. Rapid intensification hides in subtle patterns, faint clues buried in the storm's shape and surroundings that human forecasters and physics models struggle to catch. Pattern hunting is exactly what these learning systems do best. By studying every rapid intensification event on record, an artificial intelligence can learn to smell one coming, spotting the warning signs earlier than the old methods could. This tool has real weaknesses, though. Because these systems learn only from the past, they can stumble when a storm does something truly new, something outside anything they were trained on. And a warming world keeps producing storms unlike any in the record books. A tool built on history can be blindsided by a future that breaks with history. So scientists run these new systems together with the old physics models, letting each cover for the other's blind spots. Still, the arrival of artificial intelligence has lit a fire under the whole field. Progress that crawled for years is suddenly sprinting. Which raises a thrilling question. If forecasting is improving this fast, how good could it get? Where will we be in 10 years or 20? The answer scientists are chasing sounds almost impossible. A world where no storm can ever catch a city sleeping again. Imagine a future where a storm can never again explode in the dark without warning, where every city in its path gets days to prepare. Scientists are chasing exactly that. The progress already made gives them reason to hope. Remember how the forecast cone shrank, how track prediction went from a wide guess to a sharp point over a few decades. That same kind of leap may be coming for the harder problem, the storm's strength. All the pieces are lining up at once, and together they could transform how far ahead we can see. Start with the eyes. New satellites are launching with sharper vision, able to peer into storms in ways the older ones never could, watching the inner core and the hot towers in fine detail. More Hurricane Hunter flights, along with robotic drones and floating ocean sensors, are gathering the deep, hidden data that models have always lacked, especially the ocean heat and that violent layer where wind meets water, then add the brains. The blend of artificial intelligence and traditional physics models is getting better every year, learning to spot the faint fingerprints of rapid intensification earlier and earlier. As computers grow more powerful, the grid of boxes gets finer, letting models draw the small, furious details inside a storm that used to slip through the cracks. Put it together, and forecasters believe they can win back precious time. The dream is to reliably predict rapid intensification days before it happens, instead of scrambling to catch it as it unfolds. Days of warning in place of hours. Enough time to empty a coastline, to move the vulnerable to safety, to turn a deadly surprise into a hard but survivable event. In this fight, every hour of warning is measured in human lives, and the goal is to win back as many hours as we can. But there is a hard truth waiting at the edge of all this hope. The chaos never fully surrenders. No matter how sharp our tools become, that ceiling on prediction remains, the one the butterfly effect built into the atmosphere itself. We may get spectacularly good at reading a storm a few days out. We will never get perfect. There will always be a horizon beyond which the future stays hidden, a reminder that the sky keeps some secrets forever. So the goal is simple to state. Enough warning, early enough, reliable enough to keep people safe. And by that measure, the future looks genuinely bright. The scientist watching a storm in 10 years will have tools that today's forecasters can only dream of, and far fewer cities will ever be caught sleeping. Yet even as we master the storms that exist, a stranger question hangs over the science. We have talked about the strongest storms ever recorded, the record breakers, the limit smashers. But those are the strongest storms we have seen. Theory whispers of something far worse, a storm on a scale that has never touched the modern Earth. A monster so vast and so violent, it would make even the mightiest hurricane look like a passing shower. Scientists have a name for it, and the conditions that could create one are the stuff of nightmares. Somewhere in the math of storms lurks a monster that has never formed in the modern world, a hurricane so enormous it would dwarf everything we have ever measured. Scientists call it a hypercane, and for now it lives only in theory, in equations and computer models rather than in the real sky. No human has ever seen one, but the same physics that governs ordinary hurricanes says that under the right extreme conditions, a storm of almost unimaginable power could be born. The key, as always, is the heat of the sea. Everything we have learned points to one rule: warmer water builds stronger storms and it raises the ceiling on how strong they can get. A hypercane is what happens when you push that rule to a terrifying extreme. If a patch of ocean somehow got scorchingly hot, far hotter than any sea today, hot enough to make our warmest tropical waters seem chilly, the ceiling on storm strength would rocket upward. A storm forming over that superheated water could climb to heights of power that make our strongest hurricanes look tame. How strong? The theory suggests winds that could scream past 500 miles per hour, more than twice the speed of the most violent hurricane ever recorded. A storm whose clouds would punch far higher than any normal hurricane, blasting up through the top of the weather and into the calm upper atmosphere and even beyond. Next to a hypercane, the mightiest hurricane in history would look like a gentle afternoon shower. What could ever heat the ocean that much? Here the story turns to disaster on a planetary scale. Scientists imagine a giant asteroid strike slamming into the sea and dumping unthinkable heat into the water. Or a monstrous burst of underwater volcanic activity, cooking the ocean from below. Events like these are rare almost beyond comprehension, the kind that strike a planet once in many millions of years. Yet Earth has suffered such blows before, in its deep and violent past. Some scientists have even wondered whether hypercanes played a role in ancient catastrophes. When a massive asteroid struck the Earth long ago, around the time the dinosaurs vanished, the impact may have superheated patches of ocean enough to spawn these theoretical giants. Swarms of hypercanes could have blasted water vapor high into the upper atmosphere, damaging the layer that shields the planet, helping tip an already reeling world deeper into ruin. This remains an idea under debate, a possibility rather than a proven fact, but it hints at just how world-changing such storms could be. For now, the good news is plain. The oceans today, even at their record warmth, come nowhere close to the temperatures a hypercane would need. This is a storm of theory and of deep planetary disaster, safely beyond anything our current world can produce. You will not see one in your lifetime, and neither will your descendants for countless generations. Still, the hypercane teaches a humbling lesson. The same simple rules that govern a summer thunderstorm, followed to their most extreme conclusion, describe a monster that could help end an age of life on Earth. The storms in our sky and the nightmare in the equations are branches of the same tree, and that connection leads to the deepest truth of all, the real lesson hidden inside every storm that breaks our rules. Somewhere over the ocean tonight, a forecaster sits in a dark room, watching a small swirl of clouds and wondering what it will become by morning. We started this journey with that same scene. A storm that fooled everyone, a monster born overnight while a coastline slept. Now, after everything we have seen, That forecaster looks a little different to us. We understand the impossible puzzle they are facing, the deep warm water they cannot fully see, the tiny hot towers firing in the core, the chaos that blurs every future, the rules that storms keep breaking again and again. And here is the truth that ties it all together. Every time a storm defies the rules we wrote, it is teaching us something. It is showing us the exact edge of what we understand, the place where our knowledge runs out and the mystery begins. A storm that intensifies when the model said it could not is pointing straight at a gap in the science, a piece of the puzzle we have yet to solve. These rule breakers are frustrating and they are dangerous, and they are also the greatest teachers we have. They tell us where to look next. That is how all of this progress happened. Every forecast that failed, every storm that surprised us pushed scientists to dig deeper. The monster that caught a city sleeping led to new satellites. The storm that broke its speed limit led to new theories. The chaos that blurred the future led to whole new ways of forecasting. We learned the most from the storms that humbled us the hardest. Think about how far we have come. Not long ago, a hurricane was a near-total mystery, a bringer of doom that arrived with almost no warning. Today we can trace a storm across an entire ocean and point to the town it will find. We can fly into its heart, read its hidden numbers, and run its future 100 times over. We turned one of the nature's great terrors into something we can watch, measure, and increasingly predict. That is a staggering achievement, built storm by storm, failure by failure. Yet the storms will always keep a few secrets. The chaos in the sky guarantees it. And in a warming world, they are changing the rules faster than ever, growing stronger, wetter, and quicker to explode. The chase has no finish line. Every answer we win uncovers a new question. Every rule we master reveals a rule we did not know was there. Maybe that is the real lesson these storms carry. They are a reminder that nature is always bigger than our understanding of it, always holding one more surprise. We have learned to stand against them. We can see them coming now, warn each other, and save lives that once would have been lost. And we have also learned to respect them, to face the sky with humility, knowing we will never fully tame it. So the next time you hear that a storm is defying the forecasts, doing something the experts did not expect, remember what that really means. Out there over the water, a monster is teaching us the limits of what we know, and somewhere in a dark room, a forecaster is watching and learning and getting ready for the next one. Because the storm always has one more rule to break, and we will always be there, trying to understand it.